I'd like to welcome you all back onto our lesson 2 of our power transfer module. So this lesson is going to be basically looking at voltage control. So throughout the country, the power is getting controlled at a local or centralized area. And for us, it gets controlled in a place called Simmerpen in Johannesburg. So what they do, we've got control engineers that are sitting there and they are looking at what is being generated all the time. And they compare what is being generated with what is the load that's being consumed. So that would be coming from the distribution stations. They can see what load is being consumed all the time. And they're always trying to match the generation capacity to the load that's being consumed. That's why they can be able to tell the different power stations if they can be able to take off a unit or two in order to do maintenance, because they know how to parallel the network correctly in order to still meet their load that is being needed for consumption. So in the case where now we are sitting with the country back in load shedding again, it basically means that the power that is being generated, even when they include the peak power stations, which are really the stations that only come on board when the need arises. They're not always running. They sit and they only come in when we see that the load is getting bigger than your generating capacity. So with load shedding, it means even if those have come on board, because load shedding usually happens due to unplanned maintenance of an emergency that has happened in one or two of the generation power stations, you find that we have now got an imbalance. Our load is much higher than our generating capacity. So those engineers then they need to let go of some of the load, and that's why they would then inform us that we need to start having load shedding in order for them to make sure that our load never goes above the generation that the country is currently having. And the importance of doing this control really is all about managing the frequency so that we're always sitting at that 50 hertz, and that also managing our voltage in the system, that it is always consistent, especially on our bus bars that we have. Now, the control room doesn't only sit with the national one that's sitting within Johannesburg, looking at the entire country. We also have control rooms when you go to the different regions or the different operating units, as they call it, within distribution. So the group of engineering 3 last year went and visited ESCOM in Beacon Bay, where we saw the control room that just looks at the entire Eastern Cape as a whole, and it shows exactly what is the capacity that ESCOM has compared to what is the load that is being consumed by the different consumers that they have as customers. And then they are always trying to match this as well. Same principle that the Simmerpen guys are doing throughout the country. They do that also at a provincial level. So these control engineers, they always need to make sure that we are counteracting any voltage variations that are happening within the system. Because the minute your voltage varies a lot, then it means that you have an inconsistent frequency as well that can happen on your system. And this might lead to a lot of equipment being damaged and a lot of your consumers being actually off the grid due to the variations that could occur. So what we have on the pictures that you see on your right hand side, the first one is an SLD on top, single line diagram, and you can see that the blue line is your bus bar. So in there you basically have two generating stations, and they come into this bus bar, which we can assume is got a transmission, and they go through two different transformers, three of them, where they are going onto our outgoing feeders. So if you look at this and you're sitting at a guy in Simmerpen, you can see those two are two power stations, and then they come into your network grid and they go out into your transmission network where they are going to three different provinces, or maybe two provinces with two feeders going to one and the other one going to another province. Now, and at the bottom, this is how the bus bar physically looks when you go inside. So at the bottom, you can see that just next to the light in there, you've got a transformer. And from the transformer, you've got some wires that are going up. And this thing that you see where we call them lattice structures, that is really your bus bar. And the definition of your bus bar is said that it's a common connection, as you can see from the SLD. It's a common connection where you have a number of loads connected in parallel, as well as a number of your infeeds or your generation connected also in parallel, feeding these loads that you are going to have. Then, if you experience any voltage drop on your interconnectors, it means that the impedance of the interconnector and the power factor at which the power is transmitted is not consistent. So, because of the expensive systems that we run, we need to be able to accommodate voltage drops that might occur in the system, especially for short period of times, or when our network grows so much that our voltages coming in and going out are not always consistent. Then we have equipment that we put in so that they can be able to manage that voltage drop that we're having on the system. So one of them is to make sure that you are going to have a bus bar voltage where you are adjusting it such that that voltage adjustment on your bus bar must be equivalent to whatever voltage drop you are experiencing within your interconnector. In other words, they cancel each other out. Then you have what we call an on-load step changing gear on the interconnector, which are usually on your transformers. So your transformers will have various steps within the transformer. And when the control engineers pick up that there is a problem whereby the voltage drop within the interconnector is getting to be huge, then that transformer can be tapped to go higher in voltage so that it can be able to cancel out the effect of the voltage drop that is happening. Why is it called on load? So that you do not have to switch off the transformer in order for you to change its gear. So the gear, which is your tap changer, is changed while it is busy running. Then we have our voltage boost by an induction regulator, or what we call a series boosting transformer. And all that this is doing is really called a voltage regulator. And it's an equipment that you put somewhere in between on your network where your interconnector is. So when you have a long line going, you would put this regulator in there so that in case of a voltage drop, again, it does the similar thing that your on load tap changing gear transformer was doing. Then the last one is you can have what we call a synchronous phase modifier. Okay, so when you're talking about a phase modifier, it means that really what you're looking at is that your phasing of your voltage coming in must be the same as your phases going out. Remember now in chapter 1 and chapter 2 we learned that there were three phases that are 120 degrees apart. So we want to ensure that throughout your network, you get the same phases between your voltages that you have in your system. So that's what that synchronous modifier does. When your phases shift, as they sometimes do, as the network is running and your current is flowing, then this modifier will adjust or have a correction factor so that you can have at your end side the same phase displacement that you had at your beginning side. Then our voltage regulating equipment gets used to control the division of power between the different feeders that you get. And your voltage regulating equipment, which we have already stated, can then be used to control your division of power between two or more feeders that you are going to get. And then we say for our voltage boost, it can be done either by an induction regulator or by what we call a series boosting transformer. which is really the tape changer that you would get in this scenario in there. So the next couple of pages are really now going into each type of regulation and describing how this machine operates and exactly how it does the work that it needs to do in order to regulate or to boost up your voltage. So what you need to take out of this slide is that these three-phase induction regulators, really all that they do is to have a machine that can take or that can vary the voltage from a 0 point up until a certain maximum value, depending on how many turns that your primary and your secondary winding that they have has got. And then secondary, the primary winding is connected onto your circuit, which we need to regulate. So whatever is the circuit that is supplying the power to the load is where we would need to regulate. And then your secondary side is connected in series with the actual circuit. They usually resemble what we call a three-phase induction motor, where you've got a rotor that is wound, and that rotor is in a locked position, usually by means of a worm gear to prevent it revolving under the action of electromagnetic force. So here you can see that this is the connection of how this three-phase induction regulator would be done. On the left-hand diagram, you see that there is an ABC that is in big letters on your input side, and then on your output side, small letters ABC. Now, your input side is where your primary windings are at, which is your rotor, and that gets connected onto your AC supply point. Then on your small letters, which is your small a, b, and c, that's your secondary windings, which is your stator, and those get connected onto your load. And how does then this do the regulation? If you look now at the right-hand side, you can see that you've got a VA, VB, and VC. Then you've got a V slash a V apostrophe B, and a V apostrophe C. Now, if you look at the apostrophes, you can see that they have got smaller voltage values than the ones without the apostrophe. So what this represents is that the ones with the apostrophe, and you can see at the top, they've got the small letters in them. They represent the load voltages. Whereas the one with the big letters, in other words, their V's are just plain VA, VB, VC, they represent the voltages that are at the start on your supply side. So what this boosting will want to do, it wants to take your small a, b, and c and shift or and increase them in voltage such that they can equal the voltage that was on your supply side. And that is what you see in the circles. So the circles are showing that this will then boost your voltage V apostrophe A to be the same as VA at the end. And same with your B and your C phases. So this slide is still talking back to that picture that I have, but I want you to now concentrate at the last 2 points, as I've already explained the first 2 points that are in here. So in these last 2 points, it tells us that what you saw in there, not only was the voltage boosted, but there was also a phase shift that was done because your V apostrophe A and your VA were not just not the same magnitude, but they were also not sitting at the same phase. So one was a little bit behind the other one. So once this phase induction regulator has done its work, it not only boosts that voltage at the end to be the same as the voltage on top, but it also makes sure that you do not have a phase shift that is done in your system. So if you wanted to eliminate the displacement of your phase, you can do that by doing an installation of your two rotors with a common shaft. Then you would only boost the voltage and not necessarily your phases within. Because at the end of your day, your phases, even though they have shifted, they would still be at 120 degrees apart. So in this slide, they talk about now the tap changing transformer. And remember what we said here, that your tap changing transformer is usually on load, so that we ensure we don't have to switch off the transformer for us to fix the problem of voltage variation that you have on your system. So looking at the diagram at the bottom, I want you to look at where you have something written, the selector switch. On that selector switch, if you look at the round element in there, you can see it's numbered 1 up until 6. It means that it's got 6 different variation steps that you can take your transformer to be at in order for you to increase your voltage on your secondary side of your transformer. And therefore, depending on whatever is the voltage that is happening on your secondary side, you will shift it accordingly until such a point that your voltage coming into the transformer is the same as the voltage that is being experienced onto your secondary side. Then the last one being our synchronous phase modifier. So these synchronous phase modifiers are usually used to control long lines, that is lines that are above 150 kilometers. And what they really do is that they act as motors. In fact, they are motors, but they are motors that are operating under no load conditions. And by adjusting the excitation that is happening within this motor, they are then controlling what we call our reactive power that you have in your system, which is Q, so that your power factor and your voltage are controlled. Now, you remember, if you vary your Q value, then it obviously means that your power factor will be controlled, because that triangle will keep getting smaller and smaller, or bigger and bigger, depending on how you variate your reactive power.